All right, for those of you who did not get to do the styrofoam ball model with me, I'm doing a video to help you get through it so that you can have it done for your work plan. Before we started looking at the model, you should be on the sheet, and number 1 says draw Earth and arrows representing Earth's gravitational force. So that's just a review. We learned in one of our stations before that Earth's gravity, that the force pulls towards Earth, so the arrows should be surrounding Earth and pointing towards Earth. So you should have something like this. I'm going to show you a picture. So draw under number 1, and then when you're done, you should have something that looks like this. Okay? So, whoops, sorry. Should look like that. Should look like a circle with a bunch of arrows. Okay, now look at number 2 on your paper. It says to rephrase this sentence so that it can be more scientifically accurate. Gravity pulls things down to Earth. So pause the video and rewrite that. Okay, so let's check your answer. You should have said something like gravity pulls things not down to Earth, but towards Earth's center. Something like that, okay? Under number 3, it says to now go back up to your drawing under number 1 and draw a circle around the gravitational field. So the gravitational field is going to be at the end of these arrows. The gravitational field is the area around the Earth where we can feel the gravity. So you're going to draw a circle around, and it should end up looking like this, labeled Earth's gravitational field. Okay? So now we've drawn kind of a picture of it. And what the gravitational field is the area around Earth, or some object, where you can feel the pull of gravity for that object. So we're going to just be focusing on Earth for this. So within this circle, if you are an object, like so I'm this little pointer here and I'm on the arrow, I would feel Earth's gravitational pull. Now if I get outside of it, I'm way out here, I wouldn't be too far away, I would not be in Earth's gravitational field, so I would not feel it. So it's an area of potential energy, and you really don't know its effect until something like a rock or whatever gets in around Earth's gravity, and then you see that it changes the direction and the speed of that object. So you kind of see it changing kinetic energy of objects. Okay? Now we're going to look at number 4, which says look at the styrofoam ball model. So I'm going to show you a picture of the styrofoam ball model. Here it is. Okay? And if you look at it, the ball, it says now, on number 4, it says now look at the styrofoam ball model. What are the components of the model and what do they represent? So the ball would represent the Earth. And the pencils, each individual pencil represents the gravitational force. So write those down. And then the last part is all of it together, the area around the ball, including like the pencils, so all that area, imagine like a bag put over these pencils. The whole thing put together is your gravitational field. Like a football field where players play football, this is where gravity plays. It's in this field around Earth. It just happens to be like a sphere shape. All right, so for number 5, it says how are the components related to each other? So we're basically summarizing what is the purpose of this model. And it's showing the area where the force of Earth's gravity would act on an object. So if you're inside those pencils, so if you're somewhere, you're an object and you're inside those pencils, you're in Earth's gravity. So it's this area around Earth where if an object gets in there, it's going to react to gravity. It's going to be affected by gravity. Okay? So that's 4 and 5. Now turn to number 6. What happens to the distance between the pencils as they move away from Earth? So I want you to pick 2 pencils, look at them, and I've kind of pointed at 2. And if you look at their distances as you go away from Earth, what do you notice between the 2 pencils? Well, hopefully for number 6 you notice that they get further apart as you move away from Earth, right? So the gravitational force gets weaker. So this is number 7. What do you think your answer number 6 means in terms of the strength of Earth's gravitational force? So if the pencils are getting further away apart, the gravitational force is getting further apart, then that means the force is getting weaker. So the closer you are to Earth, for number 7, You're going to feel a stronger gravitational pull. Unless you get further away, then it's going to be very weak. And then if you get outside, you won't feel it at all. So distance is a factor. The further away you are from an object, the less gravitational field you will force you will feel. All right, so number 8, we're going to kind of flip away from so much the model, but talk about it. It says that we watched a video, which we didn't. But think about an International Space Station. It's this big, or you may have watched the video, I don't know, but let's just think about the International Space Station. There is a, if you ever hear about it, it's a big place where like the US and Russia and China and whatever, they come and they put their space, you know, like Space Shuttle Columbias and stuff, and they touch down there and they do a lot of experiments. So if you ever hear about an International Space Station, it's always orbiting Earth. So it's coming around here, could be in here, I don't know, somewhere in here, but it's orbiting Earth, going around and around and around. But if you've ever seen a video of anyone on it, like an astronaut, they're always just floating around inside. So do you think that the International Space Station is inside Earth's gravity? So pause the video and write down what you think. Well, hopefully you wrote that yes, because it is orbiting Earth, it is affected by Earth's gravity. Otherwise, Newton's first law, it would have just keep moving away from Earth. It would just keep going in a straight line. But obviously Earth is affecting it because it's going in a circle. Okay? That's Newton's second law. There's an unbalanced force going on there. Now, it's not as important to know this, but why are the astronauts feeling weightless for some reason? It's the same thing as like if you've ever been on a roller coaster. When you're on a roller coaster and you kind of get in this spot where you lose your stomach, it's called weightlessness, and it's because only gravity is acting on you. There's no force of the seat pushing back on you, like Newton's third law. It's only gravity acting on you. So you're in this what's called a free fall, weightlessness. So the astronauts are kind of in that same boat, but all the time. So imagine being on a roller coaster where at that spot where you kind of lose your stomach and you feel like you're like just lost in the air. If you were like that all the time with a astronaut, that would be an astronaut. That's why they have to go through a lot of training and get used to it, because it's almost like being on a roller coaster all the time. All right, that was a little too in-depth, but for number 8, all you really needed to kind of put there was, yes, it's obviously, the ISS is obviously in Earth's gravitational pull because it is going in a circle instead of a straight line past us. All right, number 9. What do you think could happen to the International Space Station if it moved further away from Earth's gravity and closer to the gravitational field of the moon? Well, obviously, we learned that if it goes further away from Earth, it's going to get weaker, weaker, weaker. Say the moon's up here. Well, the moon is a pretty big object too, and if you get close enough to the moon, it's probably going to start orbiting the moon or even crashing into it, depending on that. So it's depending on that distance factor. It's going to have to get pretty far away from Earth, but it's going to have to get really close to the moon, because there's 2 factors here. There's mass and distance that can affect a gravitational pull on an object. All right, so the rest of it I'm going to kind of leave for you. On number 10, you need to watch that video clip that's on there and then basically summarize how it relates back to this styrofoam ball model. It's about a 3 to 4 minute video clip. Number 11, you're going to go back into the simulation we did, except this time you're going to select the option to show Earth and a satellite, and you're going to use that model within gravitational field. So if you need to, the link is up top, you can just type that in, and you can use that model to just show the satellite and push play and see if you can find evidence if it's, have a gravitational field around Earth, and then you're going to turn on the arrows and kind of see how you can tell it's a non-contact force. So go ahead. I will show you this though, just to kind of show so you can kind of check your answers. Number 4, I'm just going to put them up on the screen if you need a pause. You don't have to have exactly what's on the screen, but here's kind of what I had for 4 and 5. Here's what I have for 6 and 7. Here's number 8. 9. Okay, and then the rest of it you can do on your own.